Here we derive the vorticity equation. So in deriving the vorticity equation, we are going to make a few assumptions, which are similar to those that we've done before. First, we are going to assume that the density is constant, so that we have not just an incompressible flow, but that we have an incompressible fluid. Now, this is not strictly necessary. We can also derive a vorticity equation if we have a barotropic flow, where the density only depends on the pressure. We've had that before when we discussed Bernoulli equation, but here, just for the simplicity of deriving the equation, we're going to assume that the density is constant. Then we are going to assume that we are in an inertial frame of reference. So I haven't discussed this here too much, inertial frames of reference. That means that we are in a Galilean frame of reference. That means that we are in a frame of reference where we can impose Newton's second law. Right. So here for the vorticity equation, we are not in a non-inertial frame of reference, which are, a non-inertial frame of reference are frames of references where the effects of inertial forces, which you've seen maybe before in high school and in your bachelor, where you have to take into account the fact that your frame of reference is not inertial, which means that it's not translating at a constant velocity with respect to an inertial frame of reference. Then we are going to assume that the body forces F are conservative, and that means that they derive from a potential. So we can write F as a minus the gradient of phi, and phi usually here I use as a force potential. Up to now, in the derivation of the equations, I've always used the dynamic viscosity, but there is another viscosity which you often hear about in fluid mechanics, which is equal to the dynamic viscosity divided by the density. Usually it's represented with the symbol nu, and that is called the kinematic viscosity. Note that the units of the kinematic viscosities are kilograms meters minus 1 second minus 1 divided by kilograms per meters cubed. So in the end, the kinematic viscosity has units of meter squared per second. Okay, now recall our definition for the vorticity. We said that the vorticity is defined as the curl of the velocity field. And we represent the velocity with the symbol omega. It's a velocity field, and we defined it as the curl of the velocity field. Okay, so we've derived before an equation for the velocity, and that is the momentum equation of the Navier-Stokes equation. And so if you want to have an equation for the vorticity, then it makes sense to simply take the curl of this equation. Right, so we're going to take the curl of this equation, and what we are going to do is to look at every single one of these terms and see how they are transformed. So the partial U term, the U grad U term, the pressure term, the viscous term, and the body forces. Okay, so let's look at the unsteady term. So we have the curl. Remember that in this nabla we have the gradient, the pseudo-gradient vector. So those are spatial partial derivatives. The curl of rho partial u partial t. Now our variables are independent, so we can switch the order of differentiation. We can switch the time derivative with the spatial derivative, and therefore we get rho times partial t of the curl of u which is simply equal to rho partial over partial t of the vorticity. So we already have the vorticity appear in that term. Now let's look at the second term, which is the curl of the rho u grad u term. Now this is again tensor analysis, but you have formulas for all of these differentiation. So you have here the curl of u grad u. So you can go into Wikipedia and look for how you do these derivations. Those are just compositions of differential operators. So I'm not going to go into the details. I'm just going to write directly what this is equal to. So the density is constant, so it remains out, and so you can expand this term as the sum of all of these terms. So let me take these one by one. Here, this term is equal to rho, and this is u grad. We recognize the vorticity. Here, we recognize the vorticity grad u, so this is minus rho the vorticity grad u, and finally this is the divergence of u times the curl of u, and this divergence of u is equal to 0 because the flow is incompressible. Remember that we are always within incompressible flows here in IFD, so this whole last term is equal to 0. So the u grad operator we've seen before, and so this term is not so different in terms of the analytics. So this is a vorticity grad, a omega grad. So when you write this term, you just have to replace the u's that we had before by omegas. So here is how this term looks like. So it's just equal to the x component of the vorticity partial u partial x plus the y component of the vorticity partial u partial y plus the z component of the vorticity partial u partial z. And for the second component, you replace u by v, and for the third one, you replace u by w. Note, I didn't say that before, but note that all of these, you're taking the curl. Well, when you take the curl, there should be a bar here. When you take the curl, you don't change the order of the tensor. So you take the curl of a vector, and you still have a vector. So all of these are vectors. This is a vector, this is a vector. So here, this is not a matrix. You have pluses here. This is a vector. Okay, so now let's go on to the next term. Let's take the body force term. So that was our fifth term. So there we took the curl of the body force, right? And that was minus the gradient of phi. And so here it's important to remember what the curl is and what a potential is. So the gradient of phi here is our body force F, right? And remember, what does it mean for a force to be conservative? A force is conservative if it doesn't produce any work on a closed trajectory. So your force is conservative if you start from a position and then you take a closed trajectory, and when you go back to your initial position, the work was equal to 0. This is the definition of a conservative force. That here is the work on a closed contour. Now, if you use the Stokes theorem, which we discussed before, that would simply mean that the flux, here you can use the Stokes theorem, just like what we did for the velocity field, replace F by the velocity field, and then you can write that the flux through a surface which is attached to the contour C. If we take the flux, so that is n dot n of the curl of F. Those two, this term and that term, are equal, and therefore you know that this here has to be equal to 0. And here you directly see one other way of expressing that a force is conservative is simply to say that the curl, because we chose an arbitrary C and therefore an arbitrary S, the curl of f is equal to 0. And that's true always. The curl of a gradient is always equal to 0. So you know that for forces, right? So this is equal to 0, but that's just a mathematical formula. This is a mathematical result from tensor analysis. The curl of the gradient is always equal to 0. Okay, and you've seen that before in the context of conservative forces. Okay, so we can look at the next term, the third term, that was the pressure term. There we had the curl of the gradient of the pressure. Therefore, here again you have the curl of a gradient, and therefore this is equal to 0. So the pressure term disappears from the equation. Finally, we have the last term, and that was the curl of the viscous term, which has the Laplacian of u. And now this is another result from tensor analysis, but the curl and the Laplacian, they commute. So the curl of a Laplacian is always equal to the Laplacian of the curl. So we can write this term as the Laplacian of the curl of u. And of course, the curl of u is the vorticity, so this is just the Laplacian of the vorticity. Okay, so if we summarize all of our terms, we end up with the vorticity equation. The density disappears from our equation, and then we have the first term. Actually, let me keep the density for just now. So the first term is rho partial the vorticity partial t plus rho u grad times the vorticity. And then remember that we had this minus rho vorticity grad u. So this term I'm going to put on the other side of the equation. The fourth term is simply mu times kinematic viscosity times the Laplacian of omega of the vorticity. And the body force term disappeared, remember? The body force term is equal to 0. So here, this is the equation that you obtain when you take the curl of the momentum equation, and that is the vorticity equation. Note that you can get rid of the rho's here, divide everything by rho, and then you have mu divided by rho, and that is the kinematic viscosity. Here, the kinematic viscosity. So here you recognize the material derivative, so we can even simplify this further and write this as the material derivative of the vorticity is equal to the vorticity grad u plus nu plus nu times the Laplacian of the vorticity. And so now we're going to discuss, deduce from this equation how is vorticity transported, and that will give us a sense of that will give us an idea of how transport of vorticity occurs. This term here is the material derivative, so it tells you how the vorticity changes as you move with the flow, with a material element. So that represents, in terms of transport, that would represent how vorticity is advected, so how vorticity is carried with the flow. So that's really, that really here represents how vorticity is transported with the flow. This term here is you will recognize it from advanced heat transfer, is a diffusive term. Here mu has units of meters squared per second, so it's a diffusion constant. So this term here represents the diffusion of vorticity. And this term here we will discuss at the very end. We won't see it too much in our in IF day, but that would, I'm going to call this a source term, and we'll discuss it towards the end of the lecture.